In this video, we're going to explore the relationship between two of the measurable quantities that can be used to describe a gas while holding the other two variables constant. The two quantities that we will be investigating are volume and temperature. We'll make volume our dependent variable and see how it is affected by temperature, which we will vary on purpose, making that the independent variable. For good experimental design, we'll have to control the other two quantities that can be used to describe a gas, the pressure and the number of particles. Pressure should be pretty easy to control because we'll be working in a short amount of time, and the atmospheric pressure in the room shouldn't vary much at all during the time that the experiment is taking place. Number of particles, we can always control that by just making sure that our quantity of air doesn't include any leaks, so particles can't get out or new particles can get in. Here's the equipment I'll be using for this experiment. We'll use a thermometer to measure temperature, and this will be immersed in a water bath. Also immersed in the water bath will be this tube, and you can see that there's a little bit of oil in here. There's a plug of oil that's been inserted in this tube, and the bottom of the tube is sealed up. So this just makes a bubble of air. That's our volume. Because the oil is at the top and the glass at the bottom is sealed, this means we are not allowing any particles to leak in or out. So our constant number of particles condition is met. And this is all going to be immersed in a water bath that's being pressed down on by constant pressure. And so that means that the constant pressure requirement is also being met. This will be on top of a hot plate. We'll turn on the hot plate and allow the temperature to rise while tracking the temperature with the thermometer and then measuring the length of the bubble. Now, this doesn't actually measure volume directly. It measures the length of the bubble, but since the glass has a consistent diameter, the length of the bubble is proportional to the volume, and so it works just as good for investigating how volume is going to expand or contract when temperature changes. When I did this experiment, varying the temperature from 25 degrees up to 95 degrees, and looking at the length of the bubble in millimeters, I found a pretty consistent linear relationship between the two quantities. Correlation value is 0.9987, which is pretty high, which means that there's a straight line relationship. You might expect that as the temperature increases and the particles are moving faster, they would require more space. So it would make sense that the volume would increase. When the temperature decreases, that would also cause the volume to decrease. And when the temperature reached zero, in other words, there was no movement of particles at all, we would expect the volume to also be zero. In the video on temperature and pressure, we realized that when you use a temperature scale that has negative numbers in it, you can't expect that zero temperature would also mean zero particle movement. So we realized that we needed to find out what was the lowest possible temperature that there is by extrapolating this line. When we do that, we find out negative 258.2 is where this line crosses the horizontal axis, which would mean where there's zero volume. Now, of course, this isn't really zero volume because the particles themselves would take up some space even if they weren't moving. But their space will be very small compared with the space that's between them when they are moving. And so this is a pretty good estimate of what absolute zero is. Better measurements with other experiments show us that absolute zero is negative 273.15 degrees C, and when the temperature scale starts there, we call that an absolute temperature scale. In particular, it's the Kelvin scale, and that is 0 degrees Kelvin. Using that temperature scale eliminates the vertical intercept that would be present in this line if we were using the Celsius temperature, and so that allows us to reach this conclusion. The volume and the temperature are directly proportional to each other. This is only true, remember, when you're using absolute temperature, the Kelvin scale. Now, the constant that we get, the slope of the line that we just saw, depends on our particular bubble of oil at our particular pressure. So it doesn't have really universal applicability, but we can get a universal relationship by dividing both sides by T. So what we see there is that the ratio of volume to temperature is constant. This direct proportionality means that whatever happens to the volume, the temperature must have also experienced that same effect, and vice versa. So we can conclude from these findings that volume and temperature are directly proportional to each other. The effect that temperature experiences will be the exact same effect that volume experiences, and then we can use that to make predictions in calculating.